Górecki, sorry, from QuickerSim, and this presentation is about the fastest 3D thermal simulation of battery packs, model order reduction, and holistic level, system level modeling. Bartosz is the CEO and founder of QuickerSim. He holds a PhD degree in computational fluid dynamics and has been educated at Warsaw University of Technology, the University of Technology in Aachen. He attended HPC courses at the supercomputing centers in Stuttgart, Munich, Gothenburg, and Bologna. And currently he focuses on business development of QuickerSim's e-mobility software. Also, he works with German OEMs on applications of QBAT and with large software vendors on coupling of QuickerSim's simulation model with software packages established in the automotive industry. So, Bartosz, the stage is yours.
Yeah, but we need to wait a minute because the computer is frozen and we're not ready.
Oh, the whole computer is frozen. Okay, then without it. Yesterday I broke the display of our booth, so we have to work without a booth, without a display.
That happens. But I hope to relate a bit to the presentation that we had just a minute ago about the battery optimization and the generation of the data for machine learning, although we do not do machine learning at the moment. I'll hope also to answer Axel's questions about the Grand CAE Challenge when it comes to battery simulation. Okay, perfect.
So the name of your company is QuickerSim.
It is QuickerSim. Okay, and I think the title of the presentation is also a bit provocative because it says the fastest 3D thermal simulation model of battery packs, and there's always a good question: what is the best, the fastest, and should you really trust words like that? But I hope that you will be pretty much convinced with this presentation that at least it's not the slowest one that you can find. And because, well, Mark already mentioned, our company is called QuickerSim, and we've been always focused on solving these simulation challenges quick. Let's be quick this time as well, and let's start with the conclusions. So I think this should get some of attention because we're just before the lunch break, and it's difficult to get your attention probably. Let's start with the conclusions. The conclusion is that if you're interested in thermal modeling of a battery pack like that, I call it already pretty complex one, and you want to take into consideration all the geometrical details like that of the battery pack, and simulate 30 minutes of the driving profile, so having three-dimensional thermal simulation of a battery pack for half an hour of driving. Let's have a look at how long should it take if you take a pretty usual desktop computer and you generate a mesh that consists of 9 million elements. What would you expect?
3 years. Or even more.
102 seconds, like 1.5 minutes. And I will try to explain in the next slides how we do that and how that's possible. Let me first relate to what is the CAE Grand Challenge of battery simulation. And when we are speaking to different OEMs and our customers, what we see very often that the challenge is really connecting somehow things that happen in the concept phase, and here we usually speak about 0D, 1D simulation, and something that happens in the series development where mainly the accuracy comes into play, and there is like large need to do 3D CFD predictions. But to be honest, it's not the largest challenge. The largest challenge will come in a minute. However, when talking about 0D, 1D simulations, we typically speak about electric powertrain system level simulations. Very, very often the OEMs work with MATLAB and Simulink. And the challenge is how should you relate to your CFD results if you design the system, you work with the meshes like that, how should you input the data from your very detailed 3D CFD simulations to system level simulations of the whole electric powertrain. And I hope we do have the answer to that. The story that we heard from one of the German OEMs that we currently cooperate with is that they obviously do have departments working on these 3D thermal simulations. They also have people working on the system level simulations, and like the largest problem is how should you couple one of the approaches with the other one. What they have been doing, and they shared this with us, is when they do have the results of these simulations, it takes 2 to 3 months of manual work of the engineer to translate the results from 3D simulations into anything that can be used on the system level with proper accuracy. Because when they just take it, there's like speaking about the response surface models, etc. We could one more, maybe very, very similar technique for reducing the model that I'm going to present right now. Let's focus first. What would a typical CFD solver do if you were in the position to solve a thermal transit simulation? Typically, you'd start with the CAD geometry, then you would generate some mesh, well, probably much more difficult than that, and you'd expect to get temperature results like that. So what happens underneath, the CFD solver needs to solve the partial differential equations for heat transfer. It does need to solve the Navier-Stokes equations for flow if you've got any kind of flow inside in the cooling channels, if you've got active air cooling, etc. And it typically does have, it typically uses one of the two discretization methods. Either it uses fine volume method like ANSYS Fluent Bus, or probably star CCM Plus as well, or it uses fine element method to discretize these partial differential equations, as most structural solvers do. If we're speaking about the fine element method, then obviously you need to represent the temperature at every instance in time, at every node in your mesh, and you use the, well, for example, linear shape functions to approximate the solution between the nodal values. In the discretized version, well, we've got the matrix notation with the mass matrix representing thermal inertia, the convection matrix representing convective phenomena, diffusion matrix representing the heat conduction, and the heat source that, when we're talking about battery packs, the heat source would typically represent heat generation in the cells. Just for the sake of the simplicity of the explanation, let me drop this convective term. We do take this into account, but it's much more difficult to understand within just a few minutes. So let me drop that and show you the idea that is generally behind the small order reduction. So let's limit our problem to just having the thermal inertia and heat conduction. To be honest, the heat source on the right-hand side does not change anything in the approach, so I've just omitted that. If you remind the trick from the partial differential equations, where you can simply assume that you can represent your function as a decomposition into where you can represent your function as a series, where you decompose your function into a product of a function that depends only on time and the function that depends only on space, and you substitute this into the original equation, what you end up with is you end up with the generalized eigenvalue problem. And we exploit this concept to run our model order reduction. To be honest, that's something that you should be very, very familiar with that, especially those of you who work with fine elements in the structural context. Because you do that very, very often for structural simulations. If you want to calculate vibrations for dynamic response, you usually do not calculate fine element response explicitly. What you very, very often do is you generate the eigenmodes and eigenfrequencies of vibrations, and you solve your dynamic problem in this eigenvector space. And we do that the same, but we do that for thermal problems. what you can see here is just the depiction of a couple of exemplary eigenvectors or thermal eigenmodes, if you wish, something that does not exist in physics, but you can generate them mathematically and use them as the algebraic vector space for model order reduction. So basically, we use such eigenvectors to approximate all the 3D temperature distributions that can occur during the time evolution of the battery pack simulation. What's the advantage? The advantage is that we vastly reduce the number of degrees of freedom for which we need to solve. Typically, well, the fine element code would need to solve for all the temperature values at all the nodes in the mesh, and it would need to do that for every time step. We need to do that just for the number of eigenmodes that we select, and we can freely select how many eigenmodes we want to take per component. Well, then we get many more eigenmodes because we've got many components, but it's usually like 100 times up to 1000 degrees of freedom less than the original formulation. What are the results? The results are probably the most important part of this presentation, and I will also underline a couple of things here. We've started with really a toy problem. I would say it's not an automotive battery pack, it's an academic case to just study the numerical accuracy. We've checked the error that we introduced due to having the model order reduction. So on the right hand side, you can see the full fine element model that has been simulated without any model order reduction. On the left hand side, this one with model order reduction with 24 modes per component, so for each cell, for each mechanical component, probably altogether like 1000 degrees of freedom here. Well, you will see differences. This red color here is different from this red color here, but I wouldn't say these are large discrepancies, especially if you have a look at the evolution of the maximum absolute error that we introduce. You don't see that the maximum error does not exceed 0.6 degrees centigrade, and if we have a look at the mean absolute error, it's close to 0.2 degrees centigrade. I think a pretty good result if we compare that the reduced model usually works 100 times quicker than the CD one and does not need to have any supercomputer, but it runs on a desktop computer. What's next? Let's take a more complex geometry. If we take that, I have already spotted at the beginning during the conclusions phase. We do have 3 different meshes, so I've taken the medium one. Right now it's not 9 million cells, it's almost 5 million elements. And let's see what happens. First of all, you need to agree to that we need to have some kind of pre-computation phase. Every time after you change something to the mechanical design, all the mechanical properties, it's like if you have designed a new battery pack, you need to run model order reduction. But if you want to change the boundary conditions, the driving profile, the external temperatures, etc., so something that happens to the operation, you don't need to run this model order reduction phase. So pretty much you do that just once after you have modified the battery pack, and then you're ready to use that. How much time do you need to spend for that? Depending on the number of modes that you select, well, usually something between 1 and 1.5 hours. That's something that you need to spend in advance. But how quick is it later on? If you want to run the simulations, depending on the eigenmodes per component that you select, well, the simulation time for half an hour of the driving profile, it varies from, let's say, 60 seconds to maybe 400 seconds. These are the results that we got for this battery pack. In many situations, we are below the real time. If we've got very complex geometries, maybe we're a bit above real time. But compared to 100 CPUs on a supercomputer and 2 days of computations or even more that a CD, so we need to use that still an advancement. What is important, then we need to have a look at, can we trust this result? So, well, if we take too few eigenmodes, well, the differences are not large, but, well, there is some discrepancy. So usually we need to take 10 or more eigenmodes per component, and then we are pretty much sure that this result should be fine. What's next? What's the impact of the mesh? We've compared what happens if we take 3 different meshes. One of them is pretty coarse, the other is medium one, and the finest is 3 million elements. What's the impact of the mesh? Well, visually, you probably will not see any differences between the temperature maps. If you have a look at the values, they are very, very much the same. What happens if we compare the simulation time? And one thing, and that's very important, obviously, if you get larger mesh, then the model order reduction time will be longer, definitely. You need to spend more time if you get a larger mesh. However, once you have reduced your model, because you work in the eigenvector space, you basically have more or less the same number of degrees of freedom. We do some tricks on the contact, so this might be not exactly the same, but it's pretty much the same. So even if you want to investigate plenty of geometrical details in your geometry, in the mesh, then you end up with a simulation time that is actually almost constant. What it means is you can build a 3D simulation model based on the CAD geometry, regardless it's very detailed design or it's the 3D design in the concept phase, and you can take it to a very small Simulink block in the MATLAB Simulink simulation and run the system level simulations, having the full 3D fidelity and accuracy of the results. Verification and validation. At the beginning of the development of this code, we have cooperated with Solaris Bus and Coach pretty much. Some of you might know Solaris. They're not the largest bus manufacturer, but they turn to be the largest electric bus manufacturer in the European Union, having produced approximately 1,000 electric buses. All of them monitor every second, 50, 100 parameters. So what we have done with them, we have compared the results from Qbot, from our software, with their online monitoring of the batteries of the buses and experimental testing as well. We have compared that also against simulations in ANSYS Fluent. So pre-processing time is cut down mainly because Qbot is it's not magic, it's simply designed to work, to simulate only batteries. So I would say the model preparation is much easier than to take a general purpose CFD solver and simplify the geometry, generate all the meshes, etc. However, the computation phase is important. Just one module of the battery pack of an electric bus, 96 electrochemical cells inside, 15 minutes of the driving profile. We needed to have 40 minutes for the reduction phase, 15 minutes for the simulation phase, whereas ANSYS Fluent on 100 CPUs required 2 days. Already with some simplifications, it hasn't been a fully transient profile. We did some tricks to have ANSYS Fluent quite quick, because otherwise this would have been months probably. Does it really work? Again, you will see the differences. This one is CFD from ANSYS Fluent, find volume solver, Qbot find element solver plus model order reduction. You will see some differences. I would say the discrepancy is probably not very large if you take one of the lines at the cross section and it's not a properly selected line. And if you compare that, it needs 2 days on 100 CPUs. This needs just 15 minutes on a desktop computer. The same applies for the cold plate. And let's come back to what is the CAE Grand Challenge of the battery simulation. So as I said, we see that many OEMs struggle with how to couple the CFD analysis that they carry out in some of the departments with the simulations that completely different departments carry out for whole vehicle simulations, electric powertrain simulations. So there's the solution. Typically, these OEMs already do have simulation departments and CFD meshes. So let's start with the CFD meshes. Then let's import it to Qbot using the wizard that we have created that automatically detects many of the components and thermal properties. Then define some properties in Qbot, start the model order reduction, which happens automatically. And finally, well, you can leave it with in MATLAB, or you can generate a simulating block if you want to use the 3D thermal battery simulation component or simulation model in a simulated environment. That's fully possible. That's something that we currently test with one of the OEMs located here in Germany, in the south of the country. I think the most amazing part is that in a system level simulation, in Simulink, you can embed having basically a CFD simulation running on a few million nodes mesh. We do have integration with Batimo cells. If you know the Batimo company that originates from Karlsruhe, very good simulation models of the cells. So they take care of the cell modeling, we take care of the proper battery pack modeling. Some integrations, I mentioned MATLAB and Qbot already tested. We are a product partner of the MathWorks. We have also worked with SimScape, where SimScape can solve the electrical part of the battery, we can solve the thermal part. The same applies to Batimo, GNS, MS Nastran. These are basically the mesh formats that you can import already to Qbot. These two formats usually allow us to import also the meshes from StarCCM Plus or ANSYS Fluent indirectly. Developments to come to European funded project that we have at the moment, development of the simulation models of battery degradation. That's a large research project that we have right now, and a smaller one, but a very important one. We're developing the simulation algorithms for immersion cooling that are same accurate and same quick as you know. That's what QuickerSim. And QuickerSim, we are still a very small company located in Warsaw, Poland. We do have customers in Germany, in Switzerland, Sweden, in the UK, in Poland, and in the US. Just a small team of 18 people in Warsaw with both scientific and commercial background. Already more than 10 years of experience in numerical models development, and something that I have put that on the slides a long time ago. Maybe in the current political situation, this becomes a bit more interesting. Poland, in many programming rankings, HackerRank, etc., usually ranks like number 3 country in the world for best programmers after China and Russia. Second best for algorithms. So maybe it's not a very bad piece of software that we have produced. But if I come here, I would also like to ask you for something, if you can help us. So we do already have some success, but what we are looking for is we are still looking to get access and connections to more and more battery simulation departments and general simulation departments of the German OEMs, but not only German OEMs. Volkswagen, Audi, BMW, Porsche, Daimler, with one of them we already cooperate, but I can't tell with which one. Contact to professors and universities. We make Qbot available to the student teams, formula student teams, research, teaching, etc. So that's something that is extremely valuable for us, and all the other types of business partnerships that you can imagine. We've got our booth upstairs, so you can reach out to us here or on LinkedIn or through email. Thank you.
That was quick.
That wasn't quick.
Oh, you have
Still
1.5 minutes left. So, have we some quick questions before the lunch break? Other questions? Axel? Quick question.
Quick question, as usual.
1 minute, 11 seconds. Let's see.
But that's not the time for the question.
Okay.
Time for presentation.
You've shown the order reduction as one of the most important step in getting the information into your development environment. My question at the beginning was if you don't have a detailed final element CFD battery model available, what is done the other way around? For example, do you see any chance for an inverse engineering, or reverse engineering, to help to define and develop a battery in a given design space with your tools?
Well, yes, that's not something that we focus on right now, but well, we do have our all algorithms in the market for CAD geometry generation if it's a simple one, so probably for the concept phase it's fine. And we couple with the open source mesh generators. So if we are speaking about quite simple geometries, yes, definitely. What we have seen from the customers, usually that, well, very, very often they already do have meshes, and you know, generation of a good mesh is like a golden grail of any CAE. So if we see customers that already have these meshes, it's like a bit, you know, a side problem for us. But we also couple with large software vendors, also probably 1 or 2 integrations coming in the next months or year, where probably the mesh generators of these commercial tools will take that.
Okay, if you then have a simplified battery pack available in your environment, something like a digital twin, is there any opportunity to modify this in direction that it would fit into another and a new design?
Definitely. Well, if you generate that in a CAD software, you can simply parameterize. If you define that in using our CAD algorithms, that are quite simple, but you can also parameterize that and couple that with an optimizer, or maybe the optimizer that has been presented here by the previous speaker. Then obviously the optimizer should decide how to change the parameters.
Okay.